Embabel is an agent framework on JVM that mixes LLMs and domain models. It enables you to integrate sophisticated agentic flows into your application, guarded by strong typing and your own code. Let's introduce it into the existing application and see it in action. Embabel lets you build agentic workflows on the JVM using the concept of goals, actions, and conditions. The highest level is the goal. It is the result that the agent is trying to achieve on behalf of the user. To achieve this goal, the agent uses actions. Actions are defined in methods annotated with the action annotation. Some actions can use LLM, some are just deterministic steps like database query, validation, some calculations. That's just plain Java code or Kotlin. An agent plans the workflow to achieve the goal, but it does so independently of the developer. A plan is formulated dynamically and reassessed after each action. There are also conditions that the agent observes during the planning. This architecture is what makes Embabel the great choice for enterprise JVM applications that want to benefit from agentic AI. So, what do you get specifically? Sophisticated planning. It adds a real planning step using the non-LLM algorithm. Extensibility. You can add new domain models or actions without having to rewrite the code. Strong typing and object orientation. Prompts and code interact through domain objects. LLM mixing. You can easily combine various models for cost, privacy, or performance trade-offs. In addition, Embabel is designed on Spring and JVM. It means that it can benefit from the existing enterprise features and be testable end-to-end. But what's the difference between Embabel and Spring AI? With plain Spring AI, you orchestrate the loop yourself. You write the prompt, you call the tool, then you write another prompt, then you call another tool, and so on. With Embabel, you declare capabilities or actions, and Embabel infers the plan based on the input and output types and replans as it goes. So, on the one hand, you don't have to babysit Embabel as it plans its actions to achieve the goal. On the other hand, there are guardrails in your code that prevent LLM hallucinations. Embabel can be easily integrated into the existing applications, and that's what we are going to do. For our demo, we will take an existing app. It is cyberpunk themed, and it stores civilians and their implants, and also collects the monitoring logs from the implants and gives some stats on the implants. What we want to do is introduce the incident triage workflow. For instance, somebody reports unusual telemetry in some place and time window, and the system turns that into the full incident case with risk assessment, affected implants, blast radius, and containment plan. The code of the demo is available on GitHub, the link is in the description, so you can pull the project right now to follow along, or later for copy and paste code examples. Okay, let's first add the dependencies. You can use Embabel with different LLMs or even mix them. We will use it with Ollama, so we need Embabel agent for Ollama. We are also going to run this application in a shell, so we will need the Embabel shell starter and also Spring shell starter. You can also use the MCP starter or basic starter. As we will run the app via the shell, we need to disable the Spring web application and enable shell interactive mode. Also, in the properties file, you can configure Embabel. For instance, you can add the default model it will use. Let's start with something basic. Right now, we are not showcasing Embabel's powers, but rather getting to know the framework. No worries, we will enhance this logic later on. We will add a single action at first, just for simplicity's sake, and this action is also going to be the end goal. The agent will receive the user input as a string and output the incident assessment object. For that, it will parse the user input into the incident signal object, find all affected implants in the database, and calculate the risk level. The only LLM-related task here is to parse the input. The database lookup and risk assessment are written deterministically in the code. The output of the agent work is also a Java object, a risk assessment. When you output objects, it provides more reliability to the agent's response. Let's create a class called incident triage agent. The agent annotation on the class level marks this class as an Embabel agent component. In practice, it's also Spring Bean. The description is the metadata used for discovery, documentation, and potentially for planning the selection while multiple agents exist. The description in this annotation is a metadata used for discovery, documentation, and potentially for planning or selection when multiple agents exist. So Embabel knows that this agent can investigate telemetry anomalies. Then we inject implant monitoring log service. It is the tool here, but not an LLM tool. It's the domain service that queries MongoDB. You know, Embabel is totally okay with your action calling a normal service. As I said, we'll keep it simple at first, and the action is going to be one method that achieves the goal. Two annotations are important here. So the action annotation, this means that the method is an executable step in Embabel's world, and achieves a goal annotation. It means that this action is also considered a goal completing action. It means that when the agent produces the incident assessment, it means that it's done for the described goal. The input parameters are the user input, which is the raw user message from command line, from the chat or anywhere else. And the operation context is the Embabel runtime context. This is how you access AI features. In this method, we return an incident assessment object, which is the structured output of the action. In the method, we first use LLM to parse the input into the incident signal object. What we do here is that we send the prompt and user message to the default LLM configured for the application, and it asks the model to output something that can be deserialized into incident signal class. This is important because instead of getting the unstructured blob of text that you can regex away until the end of times, you get a typed object with fields like a longitude, latitude, local date time from and to, and so on. So we are basically telling the LLM to behave like a parser. Then we deterministically query MongoDB logs using our domain service, and then we classify the risk also deterministically. After that, we build the incident assessment object based on the data we retrieved and calculate it and return it to the user. And this is the output of our command. But this is too easy. Right now we are using Embabel as a fancy JSON parser, which is a total overkill. We want to truly see its power. And that means goal-driven planning across multiple types, tool boundaries, adaptive replanning. For that, we should turn our current one-step triage into a multi-action incident workflow. In this case, the agent will choose what to do next based on the data it received and based on what it learns after each action. First, let's enrich our incident domain model and add some classes. We have three new enums: hypothesis type, risk level, and step type. Then we have the incident signal record, where we pass the longitude, latitude, radius, time window as a local date time, the metric that we are interested in, or rather where we saw some anomalies, and also the threshold for this metric. Then we have the incident assessment class, which consists of incident signal, the number of logs, and the risk level. Then we have the affected implant with a serial number, a lot number model, civilian national ID, and anomaly score. We also have a root cause hypothesis with the hypothesis type, confidence, and the list of evidence. We have estimated blast radius with the number of affected implants, lots, models, geo summary, and time summary. Then there is the containment plan with the list of containment steps with the Boolean, whether the plan requires approval or not, and the estimated blast radius. The containment step is just a string for the simplicity's sake and for the demo sake. And then we have the final class, which is the incident case. It has the ID and the creation date. It also includes the incident signal, incident assessment, the list of affected implants, root cause hypothesis, and containment plan. Now let's turn our agent into the pipeline that takes the user report and turns it into the full incident case. First, we need to divide our initial method into several and then add some more actions. So the first method is going to be parse incident signal. This is the action and this is the entry point. It takes the raw text from the user and then calls the default LLM to parse the input into the incident signal. In the prompt, we specify several rules. They're very important because they constrain the output. So for instance, latitude and longitude should be within the valid ranges. For time, we use local datetime format. The matrix must be one of the 3 allowed values, and the threshold must be a real number. As a result, we go from unstructured text to a typed object incident signal. The second step is to pull the logs and compute the risk level. The triage incident method takes the incident signal that we received, and first it calls the extract logs method, which queries MongoDB logs with the location, radius, and timestamps, and that comes back as a map where the key is the implant serial number and the value is the list of logs for that implant. Then we classify risk with the classify risk method. This part is pure Java, no LLM, so we count how many implants are involved and how many log entries exceeded the threshold for the chosen metric. And then we apply deterministic thresholds, critical, high, medium, and low. Finally, we return an incident assessment object. The third step, or the third action, is to find which implants were affected and rank them. So find affected implants also calls the extract logs method. Then it converts each map entry into the affected implant. And for each implant, we compute an anomaly score and enrich the record with the domain data for lot number, model, and civilian ID. Then we sort our implants by anomaly score descending. So now we know who is affected and what is the worst situation. The next step is to generate a root cause hypothesis. Here we use LLM again for reasoning. The inputs are the incident signal, the risk assessment, and the top 10 affected implants. The LLM must return a typed root cause hypothesis with the enum type, confidence, and a short evidence list. And that is intentionally bounded, so we don't want it to write the essay. It must pick a very structured hypothesis. Then we generate a containment plan in the next action. Here we also use LLM, but with the constraints. So first we decide whether the plan needs approval, and we require approval if the risk is high or critical, or the hypothesis looks like the attack pattern. Then we estimate the blast radius in the estimate radius method. That produces how many implants were affected, up to 5 lots, up to 5 models, geo summary string, and the time summary string. And then we call the LLM again and force it into a structured containment plan. It must provide from 4 to 8 steps and short imperative instructions. So as a result, we get a usable plan. And finally, the final action is to assemble the incident case, and that is also our goal. So this method, build incident case, is marked with achieves goal. This is this done step, right? It produces the final output that we are looking for, the incident case object. It bundles everything that we learned and that we assembled: ID, timestamp, the original signal, the assessment, affected implants, hypothesis, and the containment plan. So as a result, one user message becomes the complete incident ticket. LLM is used for parsing, hypothesis, and planning the containment. Java handles everything else: querying, scoring, and rules. And that's the whole point. The agent is smart, but not uncontrolled. We can see here that the program has generated an incident case for us. Here we see the initial incident signal parsed, then goes the incident assessment with the vital information, then comes the list of affected implants with the serial numbers, lot numbers, model, civilian national ID, and anomaly score. Then comes the hypothesis with the evidence which was generated by the LLM based on the data it received and calculated. Then we have the containment plan with 4 steps, also generated by the LLM based on all the available information. And finally, we have the estimated blast radius with affected implants, geo summary, and time summary. In the end, we get the information for the developer, which is the LLM that was used, the number of tokens, and the total cost. I encourage you to try out Embabel in your own project and see how it can give some AI spice to your application without the hype. And also, don't forget to like this video, subscribe to our channel, and until next time!